Okay, so there's no one here, but for purposes of recording it and keeping it all together, I'm going to just go ahead and lecture. This was supposed to be done. This extra credit. So we're going to say that would be the description for the ellipsoid and cylindrical coordinates. Volume of the ellipsoid. Angle 0 to 2 pi. Angle 0 to 10. And go from negative big Z to big Z. R. Z. The R d beta. There's no theta, so integrating with respect to theta will give 2 pi. Integrating with respect to z will give 2 times big Z, so I can just write this. All right, but big Z is a function of R, so now I'm going to replace it. This is change of variable, simple use of. We need a negative 2R. We don't have it. We have a negative, or we have a positive R, so I'm going to multiply by minus 1/2. And then going to ultimately wind up having to multiply by 2/3 as well due to the power rule. And so negative 1/2 times 2/3 is negative 1/3. and 100 minus r squared with 3 halves from 0 to 10. At 10, you get 0. At 0, you get 100 to the 3 halves. 100 to the 3 halves is what?
Sorry, what was the question?
100 to the 3 halves power.
Is that 100? Is that? I just got back from, I had a paper written up.
It's 1,000.
Is that, so how would you?
2 ways, either 100 cubed, square root of that,
Okay, that's what I thought.
or do the square root of 100 and then cube it.
Square root of 100. Okay, yeah, I thought.
It's 10 cubed.
Yeah, I want the square root.
Now remember, it's going to be minus that, right? So it's a negative times a negative. There's the line. So, real simple. I think I had to lecture for 15 minutes. 20 minutes and then half hour for the workshop. I think that's what it was. I think it was 15 minutes last time. Let me just double check that. That's right. Yes, 50 minutes. So I'm going to obviously finish a little bit early and give you a little bit of extra time to work on the worksheet.
Okay.
So I'm going to change this first because you're going to have more than 30 minutes. You're going to have more than 30 minutes. That's it.
We're doing that at the end, or that now?
We're going to do it right now. So I'm going to set this to 40. Apply set it to 41. You have 41 minutes. Wait for the time to change. This feels like the longest 1 minute when you're waiting. There it goes. Man, you're by yourself, so have fun.
I can do all of them. Absolutely everything in the house.
Bro, official confirmed. Past few days, my phone has not been overburned.
That's good.
No, yeah, I think that.
Is it just your battery?
No, I'm just trying not to,
Vector fields.
leave it on charge next.
Mm-hmm.
The battery.
Vector fields are just multivariate vector functions. And then we have the gradient field, which is just a field created by the gradient of a function. This is also known as a conservative vector field, and your function f is called a potential function. Where potential functions are unique up to a constant. You have the cross partial property, where a function or a vector field is conservative if and only if its cross partials are equal. And so that would be the cross partial property for 2 or for 2 variant, and this would be for 3 variant. Brings in 2 new operations. You have divergence, and you have curl. Do you recognize these? Only 4 of the most well-known equations. Maxwell's equations. These equations govern light. They relate E fields and B fields, electric fields and magnetic fields. You do anything with electronics, they govern. It's basic physics. That's called the differential form, by the way. There is an integral form as well that we'll also look at later. Let's plot, I think we're plotting 2 vector fields. Yes. Let's plot 2 vector fields. First, the spin field. So the command is vector plot. We need the x component. And then the y component. And domain for x and y. I'm pretty sure that's all you need. But I don't like that. Let's turn the frame off, the axes on. All right, so there's that. All right, that's the one. You can define how the vectors are colored if I just turn them off. If I just turn off the vector color function, say there's none. And then we just get monotone, which is what I prefer. I'm also pretty sure I can change the color. This. Yes. And vector style, I can change that color. I also typically will use this option. Vector points to regular. Look how that's going to adjust it. So there's your spin field. But they wanted it on a circle, didn't they? They wanted it on the disk of what, radius 2, x squared plus y squared equals 4. So let's do this instead. So instead of setting x and y like we normally do, I'm going to set it this. can say that the ordered pair XY is in the disk centered at the origin of radius 2. It's, what's it? Origin. Let's say you don't want that region to be shaded in. You can turn the region and filling style off. And obviously same thing for the boundary. You can turn off the boundary as well. But if we want to keep it to show that that's what we're plotting, we can move it there. So there we go. That'll work. That doesn't look like the vector style is black anymore. Oh, well. That's just been good. Now the radial field. Vector plot 3D, and then same kind of thing. You want to do each component. And then you need your X, Y, and Z's. What do you want to do? -5 and 5? That will be all you need, and this is what we'll get. Where'd you think rotate? Yeah, not my cup of tea. I don't like it being boxed like that. That actually still makes it really hard to see the axis, doesn't it? Maybe instead of that, let's do... Yeah, actually, that didn't help. This then. Better. We can also set this off with the axes. So again, I think I'm gonna do black. I'm also going to do the vector points regular again. And now if you notice, right now, all the hours are 3D, right? You can adjust that. See, that looks much better. Let's just go Google. Yeah, that kind of looks good. So what do you notice about this particular vector field?
Right, so it's a radial.
So what do you notice about all the vectors? They're pointing away from the origin, right? So it would still be a radial field if they were pointing in, right? What are the three most common forces in nature? There's actually five. Five fundamental forces we call them.
Intermolecular.
There's two of them.
Oh, yeah. I don't know what those two are.
You're missing the most obvious fundamental force. Gravity is one of the five.
Electromagnetic.
You have electric force, you have magnetic force, which I think they usually combine in the one called the electromagnetic force, which gets us four fundamental forces. Then you have the strong and weak nuclear. Strong nuclear is to keep the protons in the nucleus. And the weak nuclear is the electrons orbiting.
Okay.
Gravity, electric, and magnetic forces. are all radial. Gravity points in towards the center, right? It pulls you in towards the center. So does electric and magnetic. They pull towards the center. Or repel towards center, right? Depending on the charge. Those are also what we call inverse square fields, right? Because all three of them depend on, where the magnitudes are determined or proportional to the inverse of the square of distance. Right, so for gravity, it's proportional to the inverse of the square of the distance away from the center. And by the way, just about all forces are what we call fields, right? Force fields. So when we typically talk about gravity, we talk about the gravity field. When we talk about electromagnetic force, we're actually talking about the electromagnetic field. Right. In fact, you have two main branches of physics, right? You have the general relativity branch, which deals with the very, very large, and you have the quantum mechanic, which deals with the very, very small. General relativity deals with gravity. Quantum mechanics deals with the other three fundamental forces. Electromagnetic, strong nuclear, weak nuclear. And you could never get those to play nice. Right, that was like the biggest problem in physics, was to get general relativity and quantum mechanics to play nice, and we call that the theory of everything. The grand unified theory. What's called string theory. String theory sucks. But string theory kind of lets gravity play with the other fundamental forces, right? Because before it was the outcast. Well, string theory allows gravity to come into the fold. Oh, by the way, gravity is also the weakest of the fundamental forces. Right? Look, I just overcame gravity. Jump, you just overcame gravity. Strong nuclear is the strongest of the fundamental. Followed by weak, then electromagnetic, and then gravity. Okay, and then, of course, there is a subtopic of physics known as field theory. But it's a different field theory than the mathematical field theory.
So what would that entail?
Physics field theory, what does it entail? A lot of alcohol. And maybe some drugs. Because it's awful. It's a lot of tensors, which is graduate level math. Tensor analysis is graduate level math.
Yeah, never.
But my favorite equation is the Einstein field equation, which is the gravity field. Oh, but by the way, since your vector fields are just multivariate vector value functions, they have partial derivatives. We want to find second order partials for a, well, how do you think you'd find, for instance, partial of A with respect to X? So if you just had a vector value function R of t, right, and you wanted to find the derivative with respect to t, how'd you do it? You want to take the derivative of that vector. What do we do?
Like that each of the partials.
Well, we're not talking about partials yet. Just ddt of a vector, what did you do?
You take the derivative of each of them.
So how do you think you'd find the partial of A?
we find the partial of intersected partial of each of it.
Yeah, it's just the same thing, it just kind of pulls in. Partial of A with respect to x would then just be, your first component would be the partial of the first component with respect to x, which is what?
Or it's one minus 4x to the third.
Now, what's the second component?
One,
No.
minus, or, yeah, minus 5.
What's the third component?
See. Up to sine 1.
Why sine?
Oh, 2xy sine. Oh.
Not differentiating
Oh,
with respect to y.
Yeah.
Now we need the second order partials. Well, I'm starting with x. I'm going to find the second order partials from x. How many are there?
4, 3.
Three. Oh, no, there's not. I'm sorry. There's only two. There's no z, right?
Oh, yeah.
This is just a two-variable function. So now, do the partial again with respect to x. What's your first component?
4y. Minus 12x. Sorry.
Second. Right? And third component. Just 2 cosine y. But now we have to do with respect to y. Right, so start with the ax and partial with respect to y.
Yeah, so it's on the other side of y.
4x, right?
Yeah, it's just
Second component, we're going to have to use product of y. E to the xy plus xy e to the xy. And then that's just going to be what? Minus cosine x. And negative 2x sine of y. Right?
yes.
Now ay, 2x squared, x e to the xy minus sine x, negative x squared sine y. Ayy, 0, x squared e to the xy, negative x squared cosine y, right? And then ayx, 4x e to the xy plus xy e to the xy minus cosine x, and negative 2x sine y, right?
Yeah.
All right, so look at that. And so look at that one that we just did. Look at that one. Are they the same? Remember Claret's theorem? Order of the mixed partials doesn't matter.
Right.
So they should be the same. Here we want a third derivative. Use Claret's theorem to your advantage. Order doesn't matter, right? First thing I'm going to do is rewrite Pf instead of using chain rule. What? X squared, y squared, z squared, negative x squared, y to the fourth, z, x, y cubed, z cubed. Is that right? And just so I don't have to keep writing, I'm going to call that G. So let's start with partial G, partial X, even though they want us to do Z first. What do you get? My partial G, partial X. What is it?
Yeah, 2x, y squared, z squared, negative 2x, y to the fourth, z, and then y cubed, z cubed.
Partial with respect to X again, what do you get?
Yeah, just 2 y squared z squared. Negative 2x, or sorry, negative 2y 45. And 0.
Now take the partial with respect to Z.
Oh,
No.
G
just did.
Oh, I see. So that's 4y squared z. And it's negative 2y before. So
And by Clairaut's theorem, that's the same as the one that we wanted. But they want us to evaluate that now, right? They wanted that 2, negative 1, 1. Well, look, there's no x's, so that 2 doesn't matter, right? Negative 1 squared is 1, times 1 is 1, so that's just 4. Negative 1 to the 4th power is 1. And 0, there you go. Right?
wait, so where do we get the point 2 negative 1? Sorry.
They want us to evaluate it at that point.
Oh, no. I see.
Divergence. Right, so we write it this way, del dot f, right? But it's not really a dot product that we're doing. But it kind of behaves like a dot product, right? Because we're going to do partial x of the first, plus partial y of the second, plus partial z of the third. That's what? 2xz minus 4yz squared plus xy squared right? And there's really no simplification we can make there, is there? So find this now. First off, before we even start, is this defined? Well, it is, right? Isn't this the gradient field,
Right.
which is a vector field? So you're finding divergence of a vector field, which you're allowed to do. Right? If this wasn't here, let's say, that would be undefined. But you can't find divergence of a scalar. So the gradient field, the first component is partial x. Second component is partial y. Third component is partial z. There's a sixth column, let's factor it out. Partial x is that first component. 6x y squared z, right? Partial y is the second component. Just 2x cubed z, right? Partial z of that third component. Just 0. That would be your divergence. I'm only showing this slide for one reason right now. This is the Laplacian operator. There's Laplace's equation. We're going to show that the radial function is a solution to Laplace's equation. And so what we want is this. We want to show, oh, by the way, this is called a partial differential equation. We want to show that del squared of 1 over r is equal to 0. Well, I'm also going to use this result, that it's the divergence of the gradient field. I don't feel like writing out that square root every single time, so I'm calling it r. That should be negative z. Oh god, this is hideous. That's right, I remember this one now. This is awful. It's actually really, really awful in terms of the algebra. So let's just not do it for right now.
Is the example in like any rulers?
And it's nothing we need to worry about. It's not particularly difficult, it's just the algebra.
There's a lot of
The algebra is a pain in the ass. So I'm just not going to do it for right now. I have my reasons. Curl. Again, we're not actually doing a cross product. We just represent it as a cross product because it behaves like one. So here's what it's going to be. Again, I'm not going to always write this out. I'm just writing it out this one time. First component, difference of your cross partials. So partial y of the z component minus partial z of the y. Your second component is going to be negative partial x of the z minus partial z of the x, but I'm going to rewrite that. I'm going to flip the order. Partial z of the x minus partial x of the z. And then the last component, partial x of our y minus partial y of the x. All that over. For x, y, z plus 4y squared z, right? Where did I get 4 from? It's supposed to be 2. I don't know where I got that 4 from. Two x squared z minus y squared z. And that last component is just 0, isn't it? There's your girl. Here's what I want you to do. And again, this is extra credit. Plus 2 points into the exam category. Prove both of those statements. In the, what is it, 25 minutes remaining. And this is a force group. So you have there's 1 point for each proof. In particular, take note of this one. Because that is important. That says that the cross product of every gradient field is the 0 vector. Or not the cross product, sorry, the curl of every gradient field is the 0 vector. So these will be due at 3:15.
So if it's
Partials,
And so I'll just show this now. Don't forget that your group assignment is due the 4th. That's Monday.
Okay.
And continue working on the green reference sheet.
I think
Next class, what we'll do is start with the worksheet on this stuff.
How should we?
10-minute break, and then it's line integrals, I believe. All right, so have a good weekend.